Right, good morning everybody. In yesterday's lecture, I started to make the transition from a very large normal modes problem to a waves problem by considering transverse motions of a very long mass spring system. And the way the transition worked was if that is the system like that, and that these are going to have displacements, something like that, then I'm putting through a smooth curve through these points, which has the equation y of xt, and the actual displacements yi of t are defined to be y of il t, where this is I equals 1, 2, 3, 4, 5, 6, and this distance here is 7L. And so we had to find the normal modes of the K matrix, which had the... And the K matrix turned out to be banded with only elements on the diagonal and above and below the diagonal, which means that most of the equations for the normal modes, so this is Kc equals lambda c, and most of the equations had the form 2 Ci minus C I minus 1 minus C I plus 1 equals lambda L over T0 Ci. And the only exceptions, so that will be true for 2, 3, 4 and 5, but for 6 there isn't an I minus 1 in that case, and there isn't an I plus 1 in that case, and so 2C1 minus 0 minus C2 equals lambda L over T0 C1, and in this case 2Cn minus Cn minus 1 minus 0 equals lambda L over T0 Ci. And we found that if we put Ci equal to sine I phi, that satisfied that equation. Phi is so for any value of phi, and the corresponding value of lambda would be T0 over L 2 minus 2 cos phi. So what's happening is we're effectively extending this function so that it passes through the origin. And that's giving us a clue as to what's going on, because in this case, C0 is effectively 0, and so what we require is that this is also 0, and then this will also... So the reason it satisfied this equation was because this 0 here is standing for C0, and C0 is 0 because we've chosen a sign. Because this was a sign... I mean, I could have used a cosine in here, and that would have worked here, but because I used a sign, then it's naturally 0 at x equals 0. So what we have to do is force it to be 0 at x equals n plus 1. So the condition on phi is that sine n plus 1 phi equals pi equals well, I need an index to label modes. J, pi. Okay. Where J is labeling. So we could have phi equals pi over n plus 1, 2 pi over n plus 1, 3 pi over n plus 1, all the way up to n pi over n plus 1. So then we can actually sketch the eigenvector. So the eigenvector corresponding to the lowest eigenvalue is that, and then we just put the masses on there at appropriate places, and that's what the eigenvector is. And then, so that's j equals 1, and then j equals 2 looks like that, and then the masses are here. 1, 2, 3, 4, 1, 2, 3, 4, and so on. And so that satisfies the eigenvalue equation and gives us the eigenvalues for the problem. If we wanted to sketch the way the frequency varies with phi, this is 2 T0 over L. This is lambda. It's 2 minus 2 cos phi is half a sine, is a quarter of a sine wave, like that. And so the frequency, 2 T0 over ml square root, is the square root of that. So this is T0 T0 over L 2 minus 2 cos phi. This, which is 2 T0 over L 1 minus cos phi, which is 4 T0 over L sine squared phi over 2. So this curve here, so the omega is T0 over 2L is 4 T0 over L square root sine phi over 2, which looks like, so that's pi, and that looks like that. And you'll observe the linear portion here, because I mentioned that if we're going to consider a really very large n, where the L is of atomic dimensions and the mass is an atomic sort of mass, then we're really not going to impose structures onto that, wavy structures onto that, with anything like wavelengths like this. So this maximum mode here would correspond to a mode where every mass was on opposite sides of the equilibrium. So that would be the highest frequency mode, and we're obviously not going to generate. We're not going to generate a structure like that. So for wave purposes, these modes up here are somewhat unphysical. This model also models acoustic waves in solids, and in that case, these K's up here are physically accessible, but you'll learn about that in a couple of years' time. So the normal modes are starting to look very like waves on strings. I want to make one further connection between the normal modes and the waves. I want to go back to the original equation So d2yi by dt squared, where yi is a function of t, has now become partial d2y by dt squared, where y is a function of x and t. Okay? So my equation of motion actually reads m d2 partial d2y by dt squared equals minus k y, which is minus k. So if this is evaluated at x and t, then the effect, the matrix acting on that produces three values of y. So that becomes minus t naught over L into 2y of x plus L t. Sorry, I said that wrong. 2y of xt minus y of x plus L t minus y of x minus L t. So the discrete equation that I started with, which is up the top of the board there, has now turned into a difference of continuous functions. And I can expand these two using a Taylor series. So y of x plus L t is y of L y of x t plus L dy by dx plus a half L squared d2y by dx squared plus higher order terms in principle. And exactly the same thing will work with x minus L, except we get a minus there. So when I add together this y of x plus lt and y of x minus lt, this term cancels. And I get twice this and twice this. But twice the y term is cancelled by the leading term. And so what I end up with is m d2y by dt squared equals minus t naught over L. That has cancelled with the leading term of that, and then we're left with minus twice a half L squared d2y by dx squared, which tidies up quite a lot to give t naught L. The 2's cancel, the minus signs cancel, d2y by dx squared. And so the equation is satisfied by the functions, any function y that's for the equation of motion. It will be d2y by dt squared equals t naught L over m d2y by dx squared. And that is a rather important equation. It's known as the wave equation. Capital T, capital W, capital E, the wave equation. There are lots of equations that different waves satisfy, but quite a lot of waves satisfy this equation, and this has quite a lot of special properties. And we're going to be spending most of the rest of the lecture course studying the solutions of this equation in various circumstances. The factor that appears here is actually the wave speed squared. So t naught L over m is equal to t naught divided by m over L, which is t naught over rho, where rho is the mass per unit length. Okay? And that equals the wave speed squared. And so that's another equation that we're going to use quite a lot. Now, I'm going to derive these in the next lecture, starting from a continuum view throughout, instead of this rather awkward transition from a particle view to a continuum. So I'll rederive both of those equations in the next lecture from a rather different standpoint. but they do, if you think about it carefully, they do emerge out of a very large normal mode system and give the right kind of properties. The reason that that is a particularly important wave equation is that the kind of simple things that we, simple wave solutions that you've written down in physics for some time satisfy it. So sine kx minus omega t satisfies the wave equation, and equally a cosine would as well. So if we differentiate that with respect to x, dy by dx is k cos kx minus omega t, d2y by dt by dx squared is minus k squared sine kx minus omega t, and similarly d2y by dt squared is minus omega squared sine kx minus omega t. When we differentiate with respect to t, we get an extra minus sign, but when we do it twice, we get two minuses which cancel, and therefore d2y by dt squared equals c squared d2y by dx squared, provided because we're going to get d2y by dt squared is minus omega squared over k squared d2y by dx squared, provided c squared equals omega squared over k squared. So as long as that condition is satisfied, for as a relation between omega and k, then all waves, all travelling waves of this kind will satisfy the wave equation. And that's why, and that's quite an important type of wave disturbance, and that's why the wave equation crops up so often. So I'm now going to leave normal modes behind and concentrate fully on waves. So let me give you some outline of the structure of what's going to happen. In the rest of this lecture, I'm going to talk about general waves phenomenon, and waves phenomena more general than the wave equation, by talking about waves which don't satisfy the wave equation. And then we shall go on to discuss the derivation of the wave equation for waves on strings and its general solution, and the application of that general solution to particular circumstances. We will look at boundaries between media where the wave equation has different constants on different sides of the boundary. We'll look at energy flow in the waves, and we'll look at some waves, which all of that will be in the context of waves on strings. And then in the final part of the series, I'll look at waves in other systems than the waves on a string, and introduce the concept of wave impedance. So that's roughly where we're going. So let me start then with a kind of definition of a wave. A number of years ago, there was actually a discussion in the journal Nature about how you could bring together all the different phenomena in physics which are described as waves. And it's actually very difficult because these phenomena are very diverse and they don't actually have that much in common. And so it turns out to be quite a vague definition in a sense. So there it is. So wave definition, and you can put that in quotes if you want. It's a disturbance of a background state and in fact the definition that I just had defined that to be an equilibrium disturbance of an equilibrium background state. which propagates and transports energy. So I'm going to put energy transport at the heart of this because that does seem to be something which the various different wave phenomena in physics have in common. The propagation I'll talk about a bit more now, and it's slightly problematic because if the wave doesn't propagate, if the wave doesn't move unchanged in form, then it's quite hard to say whether it's the same wave and therefore in what sense it's propagated. I mean, if it's a disturbance that propagates, that's relatively straightforward. The question is, can you assign a velocity to that? In order to do that, you have to tie up one point on the wave at one time with the corresponding point on the wave at a later time, and that correspondence might be quite fuzzy, and I'll show you why. So let's go to, let me introduce you to something which is linked from the lecture page, the dispersive wave packet plotter. Some of the questions on the problem set, we invite you to use this. So this just superposes waves of different wavelengths, basically, and it then shows it propagating in time. In order to do that, we have to know it's time dependent. So you actually specify a set of k's, which are the k's that I've just defined there, the coefficients of x. You have to specify a relationship between k and omega. And the relationship between k and omega that's used is not the one here, but something that does slightly shows some more interesting physics. So to start with, I just want a single wave, which I can do by putting the minimum and the maximum k equal to each other. And then it says make wave packet. And this is a picture essentially of a wave on water, which is why it's coloured blue. And if we, there's a button called video, which sounds fun, so if we press that, it just does the kind of rather obvious thing, okay? It propagates. So that's the wave disturbance on the water propagating forwards. But the useful thing for this purpose is that this is showing you what speed it's propagating at. So there's a little box, a little information box at the top of the plot panel, which says k min equals 20, k max equals 20, omega min equals omega max equals 14, that's per second. The k is per meter, and that gives you the phase velocity of 0.7. So let's just do that little sum. So we found that the wave speed was omega over k. So for this wave, k is 20, omega is 14, so that's meters to the minus 1, that's seconds to the minus 1, so omega is 14 over 20 equals 0.7 meters per second, and that's the speed. And so the bottom scale there is in meters, and that's showing what's actually happening. And if we just go back to t equals 0, and so if you look, for example, at that wave that's just coming to its maximum at x equals 0, and we click the increment t button, so that's incremented time by 0.05 seconds. So if I just click forward a bit, there's a second, and that's, you can figure out how far that's moved. So actually I've moved it too far. So if you play with that, you'll observe that there's a consistency between the picture and the displayed numbers. Now that's a very simple wave because it's just a propagating sine wave. And if we superpose different waves, so if we just superpose, for example, 3 waves, then we get a more complicated picture, and its motion is more complicated. And that's because the different waves interfere in different places at different times. But some of the the definitions I'm going to give for a general wave phenomenon, some of them apply to any wave, and some of them apply specifically to sinusoidal waves. Some of them apply to, this is a problem which I mentioned at the outset. There are very few of these things apply to all waves in all categories. That's the nub of the problem. So a typical sinusoidal sort of wave like that, I introduced this concept of an equilibrium background state. So for the wave on a string, the background state is the undisturbed stretched spring, and that's in equilibrium. There are forces at the end that are holding it stretched, and it'll just sit there indefinitely until something happens. The disturbance is the action of plucking the string, and that produces something that propagates along the string. So for a so the kinds of things that you need to have definitions for, that would be what I would call the amplitude. It's a local maximum of displacement. So this coordinate here is the measure of the disturbance, which in the wave on a string is literally a transverse displacement, and similarly for the wave on water is a transverse displacement, but it might be other things. So that will give the amplitude. It's tempting to call that an amplitude, and if you want to do that, you ought to specify it as a peak to peak amplitude. So for a periodic wave, this wave that we've got here is not simply periodic, but if we go back to our periodic wave, then we can define. So the definition of periodic, the mathematical definition, is y of x plus p t equals y of x t, strictly speaking for all x. And p is the period. So p is the spatial period, and that's known as the wavelength, and it's usually given the symbol lambda. So 1 over lambda is defined to be the wave number, which is, so this is length per wave, this is waves per unit length. For a sinusoidal wave, we can, so I'll put this in brackets because this would apply to any periodic wave. For a sinusoidal wave, we could define 2 pi over lambda, and that would be the k that I've introduced here, so that would be k, and that's called, confusingly, the wave vector. The reason it's called the wave vector is that when we generalize this one-dimensional wave to a 2 or a 3-dimensional wave, then the factor omega t remains omega t, but k dot x becomes vector k dot vector r. Okay, so this k dot x term in higher dimensions becomes a dot product, and the vector in the dot product is k. So it's not a vector in a one-dimensional example, but in higher dimensions it is. And then if the wave propagates with speed c, then we can also give our attention to one point. So if we focus on the point x equals 2, then it'd be helpful if this was going a bit slower. Let's not do that. So at x equals 2, the wave is going up and down and up and down and up and down. And so at any point there is a frequency which is usually called, what did I call the wave number? What did I call the wave number? Oh, I didn't give it a symbol. It's usually called nu bar. But you need the bar because the frequency is f, or it's nu. And then absolutely parallel with this, we can define one, well, to be absolutely parallel, we need to define the time period, t, and that it would then be 1 over t, and we can define the angular frequency, which will be 2 pi over t, or 2 pi f. So those are just standard definitions. Some of them, and this one again applies only to sinusoidal waves. And what we've just seen is that for a single frequency wave, the wave speed is c. Now let's look at that in a bit more detail. Sine kx minus omega t. What we mean when we look at the wave in motion is what we follow are the maxima or the minima or the point at which it crosses 0, and so we look at points of constant phase. Okay, so I'll call that phase psi, sine psi equals constant. Well, where does that occur? It occurs at the point psi equals kx minus omega t. And so, for example, psi, x equals psi over k plus omega over k t. So which is x at time 0 plus ct. And so that point of constant phase was at the point x of 0, and at a later time it's moved to x0 plus ct, so the wave velocity is c. So the effect of this dispersion relation, which we got out of the wave equation, omega squared over k squared equals a constant, means that all waves of different frequencies and wavelengths all travel with the same speed. So that's another very special property of the wave equation. It's a wave equation for phenomena where there is a unique wave speed, like, for example, light, the speed of light, like sound, the speed of sound, and like, as we shall see, waves on strings. But not all wave phenomena. And so this dispersive wave packet plotter is to do with surface waves on water, and in the information panel there's a load of stuff about the dispersion relation that's applicable to this particular case. Let's look briefly at superposing waves. It wasn't part of the definition that I gave you that the waves had to be linear so that you could superpose solutions, but wave phenomena normally are linear at sufficiently small amplitude, and so we can look at what happens when we superpose solutions, and we can also analyze solutions. So if we take our sine kx minus omega t, then obviously we can analyze that as sine kx cos omega t minus cos kx sine omega t, we can represent that as a difference between two product waves. And so if we took, for example, if we added to that sine kx plus omega t, so that's a wave with the same amplitude but just going backwards. And then we'd have plus sine kx cos omega t plus cos kx sine omega t. And so that two-wave superposition actually boils down to those cancelling twice that. So what sort of a wave is that? So 1. So there's the sine kx bit. Let's just put in minus sine kx at the same time. The actual displacement, we need twice it, don't we? Because it's twice that. Okay, so I've just plotted there 2 sine kx and minus 2 sine kx. And that goes on indefinitely, of course. But the actual wave is that multiplied by cos omega t, which is a number between minus 1 and 1. So the actual wave disturbance at any time is, for example, that, or that, or that, or that. So it's actually oscillating up and down between the limits given by 2 sine kx. Now that's a slightly odd kind of wave because it's not, I mean, I've said that waves propagate. This one actually isn't propagating. We've superposed 2 propagating waves and we've ended up with a wave that's not propagating, and that's known as a standing wave. And so a standing wave has no overall propagation and fixed nodes. Here's a node. Now, waves aren't just limited to travelling waves and standing waves. Those are kind of limiting cases. We'll meet quite a lot of waves which change shape as they propagate, and therefore it's not a simple propagating wave or travelling wave, and it's certainly not a standing wave. So that's the example of superposing 2 waves which are going in opposite directions. Let's do something slightly different. But these were waves with the same amplitude and the same k and omega, but just going in opposite directions. Let's superpose instead 2 waves going in the same direction, but with different k and omega. So now we're going to look at sine kx, k1x minus omega 1t plus sine k2x minus omega 2t. So these are going in the same direction, both going forwards because of the minus sign here. But they've got different values of k, and k2 minus k1 is much less than k1. So they're very similar in k vector, in wave vector, but they're just slightly different. And that is the example of a 2-wave superposition would look like. There. Can't happen. That can't happen. There we go. Right. So that's what it looks like. Let's figure out why it looks like that. Let's call that sine psi 1 plus sine psi 2. And we just use our trigonometrical addition formulae to give us twice sine psi 1 plus psi 2 over 2 sine plus sine is twice sine cos psi, well, psi 2 minus psi 1 over 2. Now, which order you put those factors at the end doesn't matter because it's the cosine. And I've put it like that because I'm assuming that this one is slightly bigger than this one. So that is 2 sine k1 plus k2 over 2x minus omega 1 plus omega 2 over 2t multiplied by cos k2 minus k1 over 2x minus omega 2 minus omega 1 over 2t. So if we just sketch that at time t equals 0, we can do very much the same approach. We see that it's a product. We'll ignore the time defect. We'll put t equals 0, so these t factors aren't present. We have this phase here is varying rapidly. We have x. The phase is x multiplied by a large number. Here, x is multiplied by a small number. So this, I'll call this the fast term, and I'll call that the slow term. So I'll do the same kind of thing that I did for the other one, for the standing wave. I'll start by sketching the slow term. So the slow term is effectively 2 sine cosine, I'm sorry, 2 cosine and so on. And then I'll sketch its negative as well. So that's what I've just sketched is the 2 and the slow term there. The actual displacement, y, is given by that multiplied by this rapid sine function, which varies between plus or minus 1, and there it varies between the two limits on the graph. And so that produces a wave looking very much like the one on the sketch. On the plot. And so suppose y satisfies the wave equation. So that is to say omega over k equals plus or minus c. So the wave equation mandated c squared is omega squared over c squared, and the plus sign is for forwards going, and the minus sign is for backwards going. So these are two forwards going waves, so we just have plus for these waves. Okay, so omega 1 over k1 equals omega 2 over k2 equals c. So omega I equals kic, and so omega 1 plus omega 2 over 2 is k1 plus k2 over 2 times c. And so the slow term, the fast term here is propagating at omega 1 plus omega 2 over 2 divided by k1 plus k2 over t. So the fast term propagates at omega 1 plus omega 2 over k1 plus k2 equals c. But the slow term does the same. So the picture looks exactly the same at all times, but the envelope and the wave inside it propagate forwards locked together. And I think, if my luck is in, exhibit that by choosing 3637. So this is a slightly higher spatial frequency, but you'll see that it's propagating forwards. It's propagating a bit more slowly than the previous example, but the envelope and the wave are both propagating at the same speed. And that's because I've superposed two waves with the same phase speed. And I don't know whether you can read the information panel at the top. It says K min equals 36, V phase is 0.232, K max is 37, V phase is 0.232. So the way this works is that the actual maxima and zeros are determined by the fast term. So the speed of the fast term determines the speed of propagation of points of constant phase, maxima, zeros, minima. So the fast term propagates at what's known as the phase velocity. It's the velocity of points of constant phase. The slow term is actually the envelope velocity, and this is known as the group velocity, and that is omega 2 minus omega 1 over k2 minus k1. Now, so given my supposition back here that y satisfies the wave equation, then omega over k equals c, and both of these propagate together. So that's a possible thing to happen, and it's exactly what does happen with, for example, sound waves. However, the first example I showed you was not like that, and that was because the dispersion relation, the relation between omega and k for waves on water, is of a different kind, and I'll talk about dispersion tomorrow.